Yeah, I'm Jens, founder of WunderGraph. Over the last couple of years, I wrote, I don't know, 90 or something blog posts. So you've probably read one of those. And because it's already kind of late, I thought we need to, we need to do something about it. And because federation is such a big topic here, I thought we play a little game before we start. And the game is named Will It Compose? So maybe you've heard about Will It Re-Render? So today we play Will It Compose? And everybody who wants to join this game, the rules are very simple. Everybody who, you don't have to, but if you like, you just stand up. And if you think it will compose, you raise your hand. And if you're wrong, you sit down. And we play a couple of elimination rounds, and we see who has an idea of federation. What do you think? Who joins me? Come on! So, will it compose? What do you think? Raise your hand if it will compose. By the way, this game was developed by one of my colleagues, David, from Manchester. He's our best engineer from Manchester. We have one in Manchester. So, the first subgraph, we run the test. I hope I do everything right. Test suite. They compose. So if you had that wrong, please sit down. Second task. We have two subgraphs. One is easy, and the second one is peasy. Will they compose? Raise your hand if they compose. Are you really sure? Are you really, really sure? Will they compose? Lee, you have your hand up. Don't disappoint me. Okay, composition test suite. Second graph. They don't compose. A valid federated graph must have at least one populated query root type. Lee Byron is sitting. What is going on? Benji! You won? No, we have three left. Okay. Now you wake up. Okay, next game. First subgraph is reality. The second one is your dreams. What do you think? Will they compose? Raise your hand if they will compose. You raise your hand? Keep it down? Last bet? Okay. That is number 4, test suite. They don't compose, and I explain why. The root type field query I have is defined in the following subgraph reality. However, I have friends is only defined in the following subgraph your dreams. Three left? Okay. I have one more. I have two more. No, 3. Winner gets a federetzel. Okay, we have entity. Do we still have federetzels? Okay, winner gets an applause. Okay, Schrödinger's entity. What do you think? Will they compose? Make a guess. You raise your hand, Benji? No? What do you say? I don't know. You raise your hand. Okay, that is the question 5. Let's run 5. They compose. You need to sit down. Okay, last 2 rounds. I hope we find a winner. With friends is the first subgraph. The second one is with husband. Will they compose? Yeah, I also don't know what that means. No. I really don't know. It's just a coin flip. I don't know, so we'll go the other route. Okay. You raise your hand, right? Okay. That's number 6. The object wife defines the same fields in multiple subgraphs without the shareable directive. The field money is defined and declared shareable in the following subgraph with friends. However, it is not declared shareable in the following subgraph with husband. We have a winner! So you might be thinking that was just a fun game, but it actually has a meaning, and we come back to that later. With that, we start our talk. Dataloader 3.0, there's a better way to solve the N+1 problem. So what do you think, how many Germans does it take? This is not comedy here. This is serious stuff. How many Germans does it take to build a fast router for federation? What do you think? Why? We're efficient and not funny. So it's 1, obviously. Okay. Last week we launched Cosmo, which is an open source replacement for Apollo GraphOS in Federation. We do schema registry, studio, blah, 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 Apache 2.0. And what is outstanding in what we do is our high-performance router written in Go. And today we talk about the evolution of this router. It is based on GraphQL Go tools, which is a library that I've built and maintained over more than 5 years now. So you can see the different stages that I took in federating queries. And for me, building like a router or an API gateway that can talk, client can talk to the gateway, and then gateway talks to whatever. For me, it was always something that was not really tied to federation, but just GraphQL, and sometime later, after I started building that, more and more people adopted federation, so I started to also add federation functionality here. So that's a bit of the history. As I said, been working on this for more than 5 years now, and over these 5 years, together with one of my colleagues, which I'm so proud that I can work with him together. Unfortunately, he cannot be here, Sergey from Ukraine. Fun fact, like 1.5 years ago when we started working together on WunderGraph, and he was our first employee, he really helped us build this out. There was one call we had with Dustin and Sergey where we heard artillery fire in the backend. That's insane. So I'm so grateful that Sergey is well, and he helped me so much. We're a team of 2 who built this engine, and over these 5 years, we have touched more than 4.5 million lines of code in the evolution of building our router. So you can see that we have accumulated quite some experience in what works, what doesn't, and most of this is obviously tests. You have probably read that before. I bring it up here because what you will see is that for a gateway, and in our case for Dataloader, sometimes if you want to go fast, you actually want to go alone. And you will see what that means in a bit. So what actually is federation? And I could have just ranted about the Apollo Federation subgraph specification, and I could have said, well, it's just 32 lines of code. That's not really a specification. Who can understand that? But I wanted to give it a bit more meaning, why we created something. So I did this little game, and as we all saw in the beginning, we don't really understand federation, how it works, how to compose. It's really hard to do that. And I think there's a reason for that, and we want to change it. The way we change it is with open federation. Federation not only for Apollo fans. That's not a rant on Apollo. The idea here is that when we started building our gateway and we started building the composition tools, we quickly realized that it's actually very hard to really to understand every detail of federation, how it works, when should something compose and when it doesn't. And from the very beginning of my own usage of GraphQL, what I really liked is the GraphQL specification. It had so many details, so many examples. When I started building my first gateway for GraphQL, I could look into the specification and it told me when would a selection set merge. And it had like examples of algorithms, how to do certain validation things. This is completely missing for federation. And so the idea behind open federation is not to go against Apollo or anything. The idea here is to document and create examples and a test suite that can test a router so that we, at the end of the day, we write down the spec and then you can create an issue and you can tell me, Jens, you wrote the spec wrong. You understood this wrong. We can fix the spec. We can fix the test suite. And we can actually say, here's a router that implements this spec. So you know what you're actually using. Because if we had just implemented an open source router for federation, you would still not know what it does. So that's why I think open federation would fit very nicely into open authorization, OpenID Connect, telemetry, tofu, weird name, but yeah. Okay, that's open federation, open-federation.org. The spec is currently not in a very good shape because we were quite in a rush before this conference. We tried to launch everything we could, and yeah. Yeah, join that initiative if you like the idea. And now let's talk about Dataloader. So when you have a query like this with top products, that gives you a list, as you can guess, and then you load inventory from another service, and you load reviews, you probably know that it might make sense to do some batching down the tree because you don't want to load all the individual items. So that's what Dataloader does. And we used Dataloader in our pre-Cosmo version of our router. We used that heavily. And at some point we realized that it's actually not a good approach to use Dataloader, and there's a better way, and that's what I want to talk about today. So in a traditional sense, when you resolve a GraphQL query, the way I always thought about that, and it's quite intuitive, and most, if not all, except GraphQL probably, GraphQL servers do it this way. A GraphQL server, when it wants to resolve a query, it constructs a JSON. And the way you construct a JSON is depth first. So like you open the brackets, and then you have an object, and when you want to create a list, you open brackets again, you create a list item, etc. So it's always depth first, and that makes a lot of sense, and it's super intuitive. Every GraphQL server does it that way. And if you build an API gateway, and you see this pattern, you think that's the right way to go. So you implement it also that way. a few weeks ago, I realized that's not efficient. It's not good. It makes the code super complex. And the solution I want to present today is something, so we implemented that in our router, and I want to give it to you as a thought to think about, is this a way you could improve your own tooling? And the simple solution is, instead of resolving depth first, what we do is we divided the resolver process into 3 steps. We plan depth first, so the red arrow. Then we load the data breadth first. And once we have loaded the data, we print it depth first again. And that makes everything crazy simple, and as a side effect, very, very fast. But the goal was not to make it fast. The goal was actually to solve a problem and make it more maintainable. Here's a benchmark. Don't tweet this, because I hate benchmarks. I hope this is not too strong language, but you can tweak any benchmark or construct any benchmark you want, and you can always make yourself look good. So this is just one reference point. I put the Apollo router 1.3 here just as a reference point to indicate that we might be fast. But this is, I can construct other tests where the gap is not that big. I'm quite confident that we are almost always faster than Apollo router. But what I think it's okay to say we're 5 times faster than our old implementation. That's where I'm super confident. And everything else, yeah, we need to benchmark better. And I just want to show with this that by making this change, we are faster than our own implementation. You might be thinking that's maybe premature optimization, because if you look at the numbers, we weren't slow. So why would we actually do that? Like, nobody asked for that. The reason is, if you look at author, think about it like that. So author is a deeply nested object inside lists. So let's say for author, we want to resolve the full address. And in order to, so that's not here, but just assume. So let's say we first have to load from one subgraph the street name. And once we have the street name, we take the author ID and the street name, and we resolve the house number. Once we have the house number and the street, we can resolve the full address from another service. And if you think about what would happen in a router in this way, you would have a lot of sibling authors that run concurrently, so they concurrently resolve. Then you actually want to batch them all together to fetch the street. Once you have the street for each of the sibling from the batch, you need to unbatch what you batched, give it to each of the siblings, merge it with the previous sibling data. Then you create the next batch for the street and for the full address. And all of that with concurrency, and all of that, if you have concurrency, you need to think about mutexes, all kinds of things. All of these siblings are blocking. So if you have ever tried to write concurrent code, you will probably know that is crazy hard to debug and understand. And this is concurrent code. Like, I really like to use a debugger, but in concurrent code, you start to print, because you cannot use a debugger anymore to debug concurrent code, because in Go you have Go routines or threads, but you're laughing when you understand it. So the reason we did this is to eliminate concurrency and to make the code more maintainable. Side effect is we made it faster. So how do we do this? I want to go a bit more into detail. So the wonderful Sergey built this amazing thing here on Miro. Okay, can you see it fine? Yes, good. That's an overview of the request lifecycle. So we pass an operation, we tokenize, we create an AST, we merge the base schema, then we validate the operation, we walk a couple of times through the AST, make sure it's valid. Then we need to obtain an execution plan. We have a execution plan cache, although our planning process is quite fast, but still we have a cache if we have many in-flight requests. And then at some point we have built a plan and we can resolve the response. And here you can see the 3 steps. So we first load the data and then we resolve the response. In our use case, to illustrate this a little bit, what's happening, we have a product subgraph, reviews, inventory, and users. Most people who see demos for Federation, you're probably familiar with this stuff. This is how our query looks like. In order to resolve it, we need some more fields, like type name and the keys, like UPC and ID. And then we can go into a little bit of detail how we would actually resolve that. So let's say we don't have a data loader. In this case, we make single entity requests. So we walk into query, top products. So we load all the top products. Here's the data we're getting back. Then we load the stock. So we make such a representations query. Then we load the reviews. And for each review, we load an author, and then here the name. If we illustrate what would actually happen, so first we make a fetch, we load the top products, that gives us 3 products, and now we walk depth first into the left outer review and load this review here. Then for this review we load a user for the second review, more user. Then we load the inventory, more review, so on and so forth, until we have resolved everything. And so that's the depth first approach. And if we look at the stats, this was one single thread. We did 14 fetches, and the latency of the whole operation is the sum of all the latencies of 14 fetches. That can take some time. There's a better approach to this. We talked about it, batch requests. So in the batch request scenario, we load 3 products at the root, and then we make one batch request to load the stock for all these siblings. We make another batch request to load all the reviews, and then for all the authors, we load the name. That sounds much better. Here are the data loader execution stats. So in this case, we have 14 threads. We do just 4 fetches, and the latency is the time it takes to load the products, then the slowest of batch load stock and batch load reviews, plus the batch load of the users. So that's definitely better in terms of time it needs, but now we need a few more threads. Here is an illustration how the data loader would work. So at the very root, we have the top products. So that's our first fetch in one thread. And then we fetch inventory. And what you can see here is the problem with data loader. Because in data loader, if you walk into the first product and you want to load the UPC, you want to load the inventory data, and then you want to actually batch all the inventory fetches together. What you need to be able to do is you need to be able to walk into the first product and the second product and the third product. So you need to walk into all of them to build that batch. And then you have something like a tick or whatever that closes the batch. So that means if you want to use Dataloader, you need concurrency. It doesn't work another way. And so if you look at these different layers, at the first layer, we have 3 fetches, and then we add a couple more here and a couple more down here. And you can see the deeper we get into the tree and the more items we have, somehow we need, the more list items we have, somehow it costs us more and more threads or Go routines or anything. And now I want to show you how Dataloader 3.0 or query compiler or the breadth first approach works. The fetches are exactly the same. So we do exactly the same thing like with the Dataloader. What is different is we walk into top products, or we load top products with our first fetch, and then we don't walk into the left outer item. Instead, we walk into all the siblings in the list. And that means we get, we call this items. We get a list of items that represents the products. And once we walk into these items again with our breadth first approach, we get another list of items of reviews. You see this here. And that means at each layer, our concurrency is actually 1. We don't need concurrency anymore. We don't need a tick. We don't even need Dataloader. So if we look at the stats, we need 3 threads. And that is only because we can fetch stock and reviews concurrently. So if we ignore that, the number of threads will be 1. And the fetches in this case is 4, so it's the same like Dataloader. And the latency is also the same. What's different is that the threads here are 3, or without that concurrent fetch, it would be 1. But there's much more to it. And I will briefly explain the implications. It might be a bit hard to follow this pattern or fully understand it, so we also constructed this diagram. Not we, Sergey actually. I'm not good at this stuff. So you can better understand what's happening. So we walk into the query, we walk into the top products, we do the first fetch, and then you can see on the right-hand side, here we have the path top products. We have this data object, and then we walk into this array. Now we have this items. We call this items. This is the siblings. And now we have 2 siblings here with UPC 1, 2, type name, product. And we do our second and third fetch to load the stock data and the entities. And now you can see when we walk down here into the reviews, again, we have 2 items. They have now constructed all the data that we need to be able to load the users. So we can make the fetch here, fetch all the users. And again, we need no concurrency because we just have an array of siblings. And that makes the whole resolver code extremely simple. We just keep walking into the tree. At each layer, we make a fetch, and then we merge the whole tree up again, and we construct a big JSON blob. We can take this JSON blob, throw it into our renderer, and render the GraphQL response. And that makes our gateway code super easy to maintain. And it has other cool effects. With that, I go back Shit, I'm too slow. It was because of the game, you weren't playing it fast enough. Okay, where's my slide? So, takeaways. Think in layers, not objects. What we can see if we scale this a bit, if we have 2 array items at depth 0, and then 4 array items at depth 1, and so on and so forth, you can see that breadth first and depth first, the unit is threads. So with our breadth first approach, the number of threads we require is always 1. And with depth first, we always have to accumulate all the threads of the parent plus the child sibling threads. And you can see this adds up a bit. And if we create a diagram, it looks like this. So by using the depth first approach, the more items in an array you have and the more depth in your query, the more threads you create. And with the breadth first approach, it's kind of O1. And concurrency is not free. It doesn't matter if you have promises or coroutines or async await or anything that has a cost. And this is my conclusion. The data loader pattern solves the N+1 problem by introducing a concurrency problem. So that's a trade-off. And in many cases that can be good, but when you're building a router for high traffic, then it might not be so good. There was this person, someone said that the GraphQL's execution model is wrong for most servers. I kind of agree, and it's also wrong for certain gateways. And my question here is, does it not affect all GraphQL servers? Not just gateways, but if you look at, I took this example from Dataloader, sorry, and you can see here, the way you spot this problem is if you have a resolver that says async await, you know there's concurrency happening. Like even if you use Dataloader and it makes things faster, there's concurrency happening. So I'm not saying it's bad, just be aware that this is happening. And there's, for example, things like GraphQL that try to solve this problem, because the moment you load data in your resolver, you cannot do anything anymore. It's too late. So with tools like GraphQL, you have a way of telling your resolver what should it actually do, and can it batch or should it batch or whatnot. That's my talk, and I want to end it with one crazy thought. We're all talking a lot about the future of distributed GraphQL, and the question here is, will there be something like a vendor or a super big vendor that builds like a monopolized service that tries to own all of our GraphQL services in a monopoly? Or is there maybe a way that we build a decentralized network of graph servers? And one thing I really like about the internet is DNS. You have a website, you announce your domain names, and there's no monopoly about DNS. And maybe, and this is just something you can take away from the conference, maybe sometime in the future we have something like a graph name server where every company could announce their graphs to the world, and then something like an AI agent could try to solve a problem, looks at GNS, tries to figure out, oh, there's the graph from Pinterest. It can make an introspection query, figure out what that GraphQL server can do for it, and the AI agent can try to solve a problem with that. So take that as a thought. If you're interested in our work, check out Cosmo on GitHub, and you can follow me on Twitter. I'm the worst founder, because there's kind of like a stigma that founders need to be super smart and always right, and they need to know everything, and I make a lot of mistakes, and I want to be a bit more vocal and public about the journey of the struggle of a founder of a small startup. If that's interesting to you, follow me. Thank you. Safe travels. Ciao. Do you have questions?
If the rows are wide enough, do you think that the earlier data loader pattern will perform better?
So the question was, if the rows are wide enough, will the earlier data loader perform better? So I talked about this with Dotan yesterday, who in the other room did some benchmarking on gateways. When your batches are too big, you run into other problems. So obviously you cannot have infinite batches. I wouldn't say the other way is better, but maybe at some point you need to cut your batches into, like you have to have a fixed window size of batch or something like that, yeah. Any more questions?
You mentioned about Cosmo and also GraphQL. Like, how would you think the new Cosmo, like the loader pattern compared to GraphQL's approach? Any pros and cons, contrasts?
So I think the way Benji puts it, GraphQL is a general purpose tool to implement or to write fast GraphQL servers. And what we did here is a crazy specialized approach to make one thing crazy fast. And that's really not general purpose. Anybody else? Thank you for joining.